And he also supports Python, Linux, and open source in general, which I really like. Yes. He's from Poland and is regularly seen at the Warsaw Python meetup. And as I heard, he's also attended from the very first edition of it. Yes, he's also recognized as an inland sailor. Yeah, and who in the audience ever saw a .pyc file? Yeah. Did you ever wonder what this file is? Or who knows what the file is for? All right, so few already know it because Konrad will explain us what really happens when the Python interpreter brings your code to life. So yeah, please welcome Konrad with his talk.
Thank you for the warm welcome, and also thank you for all the people that recognized me from the last years and said hello. That's really nice. Okay, this will be about Python's bytecode. My name is Konrad Gawda. I'm a Python programmer and trainer, and as it was said, I'm also a cloud evangelist. Well, the evangelist is a person who brings good news. That's the source of the word. So cloud evangelist is a person who brings good news about cloud technologies. And that's my daily job at Orange in Poland. So you may ask yourself, well, Orange, does it have a cloud? It's a telco provider, right? Yes, but it also has a public cloud, our own public cloud from our own servers in Orange data center in central Poland. But we also do support other clouds like Google Cloud and so on. So if any of you would like to have a virtual machine running in cloud in real center of Poland, you can come to me and talk about that. Yeah. Besides that, I'm also a video cast host for Orange that we talk about cloud and IT solutions. Okay, that was about me. Before we go on with the topic, I just wanted to check the connectivity with the audience what's the best tool to check connectivity in IT? Of course, it's ping. And this one side sends ping, and the other side responds with pong. So, well, let's try that. Ping. First one is always long. Ping. 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 Yeah, great connectivity. Let's go on. So, ladies and gentlemen, this is the bytecode, example of bytecode in Python. I've made it green to make a dramatic effect. And you may see that it looks a bit similar to assembly language. Well, Python is easy to write, easy to read, is intuitive. On the other hand, C or assembly language, low-level languages, have great performance. Well, bytecode code has disadvantages of both. So this is a tough case, the topic that we'll be talking about today, but it's good to know about that. So you're the happy Python programmer, and you have your code that you run on a Python binary, Python or Python.exe. And as a result of running that, the Python binary interacts with the external world, with console, disk, network, and so on. Well, that's in general what's running Python about. Then the interesting part is what's happening inside the Python binary, at least in CPython. The thing that does the interaction with the world is CPython interpreter, also internally called as virtual machine. Don't mix that with cloud virtual machines. That's a different thing. Similar like Java virtual machine. Yeah, we have something like that in Python. But it has also another counterpart, which is CPython compiler. And it uses abstract syntax tree and so on, but it does not compile like in C language to a machine instruction set. It compiles in a meaning that it produces an intermediate step that is simple to handle by the interpreter. So, because you may think, oh, bytecode, perhaps that's the instructions for the CPU, the machine code. No, in fact, where is the machine code in here? It's down there. The CPython interpreter, well, you may think about it as a big C program that goes over your script line by line and does what your script asks you to do. But the only detail is that instead of going through raw source code, it has it parsed and it uses the intermediate step, the bytecode. Okay, so I've said you can think about it like a big C program, and in fact, it makes sense because if you dig into the sources, well, you have a big switch, which then conditionally does things depending on which bytecode instruction is it handling currently. Of course, it's not that simple, but you may get the impression. Instructions, yes. The bytecode is composed of instructions. In Python 3.13, there were 122 instructions. And we'll now go through each of them. Okay, but I hope you will learn some of them at least. And let's take as an example a really simple function that just adds two things. Perhaps numbers, but just two things. So everything in Python is an object. So also this function add is an object. And it has some fields, like for example, under code. And under this code field, if you use your editor, your IDE, to show you what should you expect inside, well, it would give you such names, and I've already printed the values that are under those names. So if you use add under code.co name, you see that the function is called add. And there are some other useful things, like for example, what are the var names, so the argument names. And there are some flags that are really interesting. And there will be some other things that we'll make use of, but the most important part is that one. Well, that one is the raw bytecode. And if you translate it into numbers, it goes like that. And it tells us completely nothing. But there are tools. There are tools to learn about that. And now, ladies and gentlemen, this will be the pronunciation exercise, because we'll not import this, we will import this. And this is disassembler for Python bytecode, a great library that helps us to understand what's going on. And, well, you may think, okay, it has a function show code. For sure, it will show us what is the code. No. In fact, it will show you like everything else what I've shown here beside the meaning of the bytecode. Well, perhaps that's why they also change it and use the name code info. But if, for example, it shows you what are the flags, which are just some integers inside the value, and here they are decoded. Okay, but there is a function that explains you what the bytecode does, and this is this.this. So it prints into the console the instructions that the things in yellow here are the things that are inside the bytecode, those raw numbers that you've seen there explained here. And the white ones are just explanations. What is it? Where is it? Or what's the meaning of that argument? Because there are instructions and arguments. So you see there are instructions like resume, load fast, binary op, return value. Okay, seems quite legit. But beware of one thing. This instruction set and the whole language of bytecode changes over versions of Python. So what you've seen now is valid for Python 3.12 and 3.11. Before that, we didn't have resume, and instead of binary op, there was a binary add. Here it was binary add without argument. Here it's binary operation with an argument. Let's say it is add. Okay, but later on, things were also introduced, and in 3.13 and 14 release candidate, we have two instructions in one, load fast, load fast. But that was 14 RC, and we have 14, the official version released now. And ladies and gentlemen, it was mentioned in earlier presentations about the most fancy name. So my contestant for this contest is load fast, borrow, load fast, borrow. Okay, so for reason of simplicity, I'll stick to the earlier versions of bytecode. They're a bit easier to pronounce. Okay, but that was this, and it prints into the console. A more Pythonic version of that is get instructions, which iterates over the instructions and yields objects that have some fields that may be useful. So, for example, argrep says you that this is named A, variable B, this is operation add. Okay, and I will use that later on. Now you get more or less the concept. Let's dig into details with a bit more advanced function that uses some external things. Not so difficult, but we'll have some interesting things here. So I'll keep this function here in the corner so that you remember that. And here are the data. So the raw bytecode that everybody loves, and underneath the easy way, the explanation. Okay, and first thing, I will focus on the arguments because there are operations and arguments. So what is the meaning of those arguments? Also a cheat sheet with the fields of the code field of that function that you've seen before. So, for example, load const loads a constant from CO consts, and it uses index 1. So we know that this function will use some constant variables, and here is a tuple of all the objects that are constant, that are not mutable, that this function will use. And okay, it says 1, so it loads half floating point number legit Python object. Then we have load global. Please discard the null. For the sake of simplicity, we will forget about that. It just loads the math object library, and it knows that it needs to load it from global's dictionary, and it needs to get a name math. So that's from that tuple that holds the names that will be used. And later on, we have load attr. So it will load as attribute sqrt from that very math library that was loaded. And it says 2 here. And what's wrong here? Index, yeah, right. Before I said it uses index 1, and yeah, it really works like indexes in Python. And here it says 1 and 2. It should be 0 and 1. Well, in fact, if you dig into documentation, these two instructions use the lowest bit for some other reason, and it's connected with the null, and they just shift right the number, so the effective is 0 here and 1 here. Okay, so that was the mystery, but otherwise it works normal. So load fast loads a value of variable of the name index 0, check var names x, so it loads variable x. Then store fast stores variable y, load fast again, and that's more or less the meaning of those attributes here. Okay, So now another thing I need to explain before we dig into a real example is how the interpreter sees that. And with working in Python, especially exceptions, you may encounter the name frames. So what's that? In fact, each time you run a function, a new frame on a frame stack is created. So you have a main function that runs some other function, that runs some other function, and the deepest function that is currently running is the one on top. And what's the purpose of those frames? Well, each of them holds two stacks: evaluation stack or data stack and block stack. Evaluation stack is the thing that will be interesting for us because this is where the load fast, store fast, and so on take place. And the block stack, well, it keeps track of the blocks of code and their indent. So if you ever wondered how Python knows which block ends here, that's the tool that it uses. But we'll focus on that one. Okay, and a stack in programming is a simple and efficient way of using memory where you can only put things on top or take things from the top of that. Okay, so you've got the knowledge. Now it's time for us to be all of us to be human interpreters of Python bytecode. So you know the function, you have the instructions here, and we've got a stack, and we will be running this function with argument x equal to. So the first instruction for us is already done because resume does nothing. Okay, but then we go to load const. So we know where the consts are stored. So bang, we load the half into our stack. And this is a Python object. Those are the Python objects that are stored here on that stack. Okay, now we use load global, similar thing, but from other source. And just forget about the null. So we are loading the math module, a legitimate Python object. Okay, next thing is more interesting. It loads attribute named sqrt, but also it does it like that. It takes the thing from the top, so the math module, it loads an attribute from that, and then discards the math module. It's not needed anymore longer on that stack. So let's try that. Done. Okay, now simple, load fast the variable x. Done, and it's equal to, because we're running the function for 2. And now call. So we will be calling a function, but there is only one argument. It is 1. Who has an idea what could this 1 mean? Number of arguments, exactly. Okay, so we know there will be one argument, great. But what function it is? Well, the instruction takes a number of arguments, so one argument from the top of the stack, and then it knows that the next thing that to expect there will be the function to load, to use, to call. So it takes one argument and then one function, and beside that also the null that we're not interested in. So be prepared. And so it removes that stuff from the stack, and as a result, it puts on the stack what was returned. So here we have a result of this sqrt, then a binary operation of multiplication. Well, I guess you may expect what will be happening here. Let's see. Yeah, okay. Now, if you ever wondered if storing things in a variable just to return that variable later on is really done, yes, it is. So in this instruction now, because we're writing to variable y, just to return it later on, it really happens. So bang, the variable y is populated with the result that we've had on the stack, just to go to the next line, which says load fast from variable y. and then the grande finale, return that. Done. Okay, so now you know how the bytecode works. Let's go to other intriguing thing, the PYC files. So you've seen that schematic before. The bytecode is written to PYC file to save time and not parse the source another time when it's encountered. And the files look like that. It has a header. There are two forms: a header with magic number, bit field, and then timestamps and size or hash value of the source. This is important because if the source changes, that we also need to discard the cached file and rewrite it. And the magic number is really important because it says what version of Python was that. Remember I told you, different versions of Python have different bytecode, so it would blow up if it gets wrong. And you can check in your Python what is the real magic number there. When those files are created, well, they're created and the cache directories are created on each import, on pip install, and they're also prepared for you in the standard library. They come pre-compiled. Or you can create them manually with -m PyCompile, which is not that useful because compile all does the same, but works for multiple files and also for directories. For directories, it goes recursive, but it does not interpret imports. No, it's dumb. It doesn't understand imports. It just compiles all the Python files which it meets inside the directory. Okay, so let's test that. I have a simple file. I call that. Let's check the PyCache dictionary is created, and in fact, I can use Python binary to run Python bytecode directly, not the source code, but bytecode, and it works fine. So then takeaway, you can run bytecode from these PYC files. It's legitimate for Python to run. Some other things to mention. What's about UV? Well, it changes over time. Some time in this year it was producing the PYC files. Some time earlier, I guess not. So consult docs how it's working currently. Other thing is avoid unneeded imports because it needs to parse all those files and write to disk. And very thing that was very useful for me is if you're making a Docker file and you're not building a Python package to be installed inside, you just put your source code inside the Docker file, please consider running Python -m compile all dot inside your Docker file definition. That will prepare the PYC files and the container will run faster. Well, so that's Python -m compile all dot, like the whole directory. You might ask, okay, but PYC files take space. Well, in my example, in my project, they take a bit more space even than the pure code itself. But on the other hand, if you're really considering that amount of space to be crucial for you, well, you may also consider removing the PY files and running bytecode directly. That will work. That will be a bit faster. Only disadvantage of removing the PY files is the exception printouts. They will not include the parts of your source code. Well, food for thought about that. And what's about this? Because I've said about header. What's inside those Marshall here, Marshall format? Well, if you go to docs, it says it's undocumented on purpose. But there is a library to tackle with that. And if you open the file in binary mode and use marshall.load, you'll get an object which says it's a code object. So in fact, if you use a function type to turn that object into a function with empty globals here, and run it, well, it will run. So you can like run PYC files with Python directly. Yeah, perhaps interesting, but there are some other useful things to cover. Optimization. There are very different meanings of optimization. One of them is touching the compiling into bytecode. And if you run compile all with O1 or O2, it will produce optimized bytecode. And what are those 1 or 2? Those are levels. 0 is, of course, no optimization, but then 1 removes all asserts, and 2 removes docstrings. So if your Python logic depends on asserts or docstrings, well, then be prepared, because people may run that with optimization. I mean, they may do compile all, but they might also run just Python minus big O or double big O, and your asserts and docstrings are gone. So be aware about that. Exception handling, well, that's boring. Let's get on to an interesting stuff. So if you're writing a function and you're considering, well, there is a big collection because there are hundreds of or millions of types of pizzas. So should I really move that upper so it's done once before all code is running? Well, it's different in those two cases. What's the difference between those two functions? Yeah. This one has list, and this one has tuple. So in fact, this, because it's a list, it will be created each time the function is run. This is a tuple, and it will be stored in code consts, because it's a constant. It's not mutable, and it doesn't contain any mutable things inside. So good to know. It's a difference whether you use list or tuple. Perhaps not that big difference, but it's somehow reflected in the run. Okay, and the final thing, perhaps not so useful, but I consider it cool. How about modifying a function on the fly? Well, if we go to the documentations and see help for code type, it says no, not for the faint of heart. Okay, but let's try. In fact, we'll use function type, and it builds a new function. You give it a code and globals. And I used add, and I tried to run it, but I forgot to give it arguments. So in fact, it's not running, but if I give it arguments, it works. So function type creates new function that I then call, and the code object has a method replace, which works exactly like with strings. So it outputs a new object. And for example, you can ask it to replace variable names instead of A and B to X and Y. But I forgot to give arguments. But it says, okay, you forgot to give it X and Y. So it works. And if I give it the arguments, it prints the answer. Okay, that's fine. So how about modifying the bytecode? So just for reference, here is our original bytecode, and I've done the research and found that this one was responsible for adding. So 0 was for adding, and what would be 1? Well, let's try. So I replace the code with the new code, and the answer is 2. And it's a really interesting question. What operation is that outputs 2 when you give it 2, some operation 3? Well, think about it and remember your answer. And in the meantime, let's check, okay, so what will be if I try to give it different values of that number, not only 0 and 1? And you can get 5, as we had, you can get 2, 0, 16, and then wow, okay. We see that there is that symbol, that add In Polish, it is małpa. In German, I know it's Klammeraffe, right? Okay, any French-speaking person in the audience? Okay, do you know how it's in French? Okay, once again. Okay, so new words to learn from that. Okay, so now to reveal. Okay, let's get exception handling. So we now get all the numbers, but to reveal what was the mystery, what was the operator, I will zoom in. So now I will use this get instructions and argrep to see what operation that really was. And I will print that. And let's zoom the prints out. And you see that the result 2 was from ampersand, so binary AND. And you can see all the various different operators that are here for the binary operation. Okay, that was Bytecode. My name is Konrad Gawda. I hope you liked it.
All right, thank you very much, Konrad. Are there questions from the audience? Otherwise, I have a question. If I don't see, oh, there's a hand down there, but I will ask mine first. The bytecode optimizations, is it really just removing asserts? Isn't it like removing this load and save, or save and then load again? It could remove this as well? Like
no, that's only that. People invented that in early days of Python and said, okay, it will do that. And now people just stick to that.
So really
and the other things will get optimized, but they're like optimized anyway. And there are various new mechanisms in Python that, well, we would need to have another talk to cover them.
All right. So there was a question there.
My question is, any production uses for any of these tricks?
So in fact, I try to give not the hints that I use myself. So like compile all for the Docker file, or whether to use list or tuple. But those are, okay, those are takeaway from that knowledge. And using bytecode directly, well, don't do that. But in fact, people tried to do that. For example, implementing f-strings before f-strings were a thing. And if you really try, you can make a decorator for a function that messes its bytecode and even does some optimization, but my advice would be don't do that.
All right. Are there more questions in the audience? One right there in the middle. Yes.
The null you had on the stack, can you at least in 1 or 2 minutes, I don't know how much time we have, at least give a hint on what it might be useful for?
Which
the null on the stack where you just said ignore that.
Okay. In fact, that's, as far as I remember, I may be missing something here, but as far as I remember, it was whether you're running, is it a free method or is it a method of an object? Because you need to pass self somehow. And as far as I remember, instead of null, that could be an object that is the self value. So that would be it.
All right. Are there more questions?
Happily, no one asked about JIT.
I have it on my list here.
Okay, so if you're asking about JIT, it's here.
Okay. So that's all you're going to tell us about it, or?
Okay, I will try not to spend another 20 minutes on that. But in fact, in the newest versions of Python, there is an option to produce machine code, not bytecode. Bytecode is still where it was, and it's not. It's like changing in its own way. The JIT is here, so it's something completely different. It makes your code run faster, but that going after interpreter uses the bytecode.
All right. So, and you also mentioned faster startup time in Docker containers if you precompile it. But what's like the order of magnitudes that you like when you think it's worth it? Is it like in the milliseconds, or can it be up to?
I did not measure that. Okay, I've checked some measurements that people were doing. It's not that really big time because it's like I think it was like 100 milliseconds. That level of timing. It may be useful, but it also does disk operations, disk writes. If you try to compile that on the run. So I think those couple of kilobytes are worth. To save that time, at least if you're starting the container frequently.
All right. So thank you very much for your talk.
Thank you.